What if I told you that every gallon of gasoline contains traces of life that existed on Earth millions of years ago? And without it, the modern world would simply grind to a halt. Every year, humanity burns energy born from prehistoric plants, plankton, and creatures that vanished long before humans even appeared. But almost no one knows how a black, dirty mixture from miles underground transforms into a clear liquid capable of powering billions of engines. Inside oil refineries, processes unfold that resemble controlled chaos. Temperatures like inside furnaces, pressures that can tear through metal, and molecules that get broken apart and reassembled. And if you stick around till the end, you'll find out which stage of gasoline production actually determines whether your car will run or not. It all starts with crude oil pumped from underground, sometimes from depths of several miles down. This oil isn't some uniform substance. It's a complex mixture of thousands of different hydrocarbons that formed over millions of years from the remains of ancient organisms. Picture this. Dinosaurs, prehistoric plants, and plankton got transformed under pressure and heat into what now powers modern civilization. Wild fact, right? When oil gets extracted, it looks different depending on the field. It can be almost black and thick as molasses, or it can be lighter and more fluid. Mixed inside are molecules of varying sizes, from tiny gases to massive heavy components. And the refinery's job is to separate this entire mixture into useful products, one of which is gasoline. The first and most crucial stage is called fractional distillation. Crude oil gets pumped into a massive vertical tower that can reach the height of a 15-story building. This tower is called a fractionating column, and it operates on a simple principle. Different substances boil at different temperatures. First, the oil is heated to around 750 degrees Fahrenheit in a special furnace. At this temperature, most components of the crude oil turn into vapor. This hot vapor mixture enters the bottom of the fractionating column. Inside the tower, dozens of horizontal plates called trays sit at different heights. And this is where the real magic of separation begins. When hot vapor rises up the column, it gradually cools down. At each level, the temperature is slightly lower than the one below it. Heavy molecules with high boiling points condense first, at the bottom of the column, where it's still hot. Lighter molecules rise higher until they reach a level with their condensation temperature. There, they turn back into liquid and collect on the corresponding trays. The lightest gases, like propane and butane, pass through the entire tower and exit at the top at temperatures around 90 degrees. A bit lower, at temperatures from 150 to 400 degrees, the gasoline fraction collects. These are the molecules we're interested in. Even lower by temperature, you get kerosene and diesel fuel. And at the very bottom remains heavy fuel for ships and raw material for asphalt. But here's the kicker. If you just separate crude oil into fractions, you don't get that much gasoline, right? Maybe 15 or 20% of the total volume. And the demand for gasoline is massive, way bigger than what naturally exists in crude. So refiners came up with a clever way to make more gasoline from what they've got. A process called cracking. Cracking is breaking big heavy molecules into smaller ones that work for gasoline. There are a few ways to do this. Thermal cracking simply heats heavy oil to extreme temperatures around 900 degrees Fahrenheit under high pressure. Under those conditions, long chains of carbon atoms literally snap into shorter pieces. An even more effective method is catalytic cracking. Here they use special catalyst substances, usually aluminosilicates, that speed up chemical reactions without heating to such insane temperatures. Heavy oil gets mixed with hot catalyst powder at temperatures around 1800 degrees Fahrenheit, and the molecules split way faster and more efficiently. After the reaction, the catalyst gets regenerated and used again and again. There's also hydrocracking, where on top of high temperature and a catalyst, they add hydrogen under pressure, up to a ton or even 1,500 pounds per square inch. Hydrogen helps clean up the molecules, removing sulfur and nitrogen that can be harmful. This process produces the cleanest, highest quality gasoline. But even after all these transformations, gasoline still isn't ready to hit your tank. You need to improve its properties through processes called reforming and alkylation. Reforming changes the structure of gasoline molecules, increasing its octane rating, a measure of how resistant the fuel is to knocking in the engine. Low-octane gasoline can ignite prematurely in the engine cylinders, causing a knocking sound and potentially damaging the motor. During reforming, gasoline molecules pass through a series of reactors with platinum catalysts at temperatures around 900 degrees. There, straight chains of atoms rearrange into branch structures and ring molecules, which have higher octane ratings. Lead used to be added to boost octane, but it turned out to be toxic and polluted the environment, so it was phased out back in the 1990s. Alkylation is the process of combining small molecules into bigger ones, but perfectly sized for gasoline. It takes light gases created during cracking and joins them together using strong acids to make molecules of just the right size with high octane numbers. It's an expensive process, but it produces premium gasoline components. After all these transformations, different gasoline streams get blended in precise proportions to create the final product with the desired characteristics. A bunch of additives get thrown into the mix too, substances that improve various properties. Detergents clean engine deposits. Antioxidants prevent gasoline from degrading during storage. Corrosion inhibitors protect the fuel system from rust. Dyes get added so different types of gasoline can be distinguished visually. In many countries, ethanol is added to gasoline by law, an alcohol made from corn or sugarcane. Usually it's 10% by volume, though sometimes more. Ethanol boosts the octane rating and is considered more environmentally friendly because it comes from renewable sources. Though there's debate about whether it's actually that beneficial for the environment, considering all the energy spent growing the raw materials. Interestingly, from 1 barrel of crude oil, 42 gallons, you get about 5 gallons of gasoline plus diesel, kerosene, lubricants, and other products. Nothing goes to waste. Even the gases produced in the process are burned to heat the refinery itself, or converted into other useful substances. A modern oil refinery is a city of pipes, towers, reactors, and storage tanks that can span several square miles. The entire complex is run by computers that monitor thousands of parameters simultaneously: temperature, pressure, flow rates, product composition. A mistake in the settings can cost millions of dollars, or even lead to a catastrophic accident. Environmental standards are getting tougher, so refineries are constantly being upgraded, installing new equipment to clean emissions, cutting energy consumption. Gasoline production has become significantly cleaner than it was 30 or even 40 years ago, though it still remains energy intensive and has an impact on the environment. This entire complex system exists, so you can just pull up to a gas station, stick the nozzle in your tank, and fill up in a couple of minutes. Behind those few minutes stand geologists searching for oil, engineers designing wells and refineries, chemists developing catalysts and additives, technicians keeping equipment running, drivers delivering fuel, a global industry working around the clock to keep the world moving. And while there's a lot of talk right now about electric vehicles and renewable energy, gasoline will remain the primary fuel for billions of cars around the world for a long time to come. It's the product of a century of engineering thought, chemical research, and technological innovation, transforming ancient organic matter into the energy of today.
Every year, humanity extracts over 2 billion tons of iron ore from Earth's crust. Picture this: more than half of our planet's entire weight is iron, most locked in the core, creating the magnetic field protecting all life. But here's what shocks engineers worldwide. We're standing on the most abundant metal in the universe, yet accessing it requires temperatures hotter than volcanic lava. How does rust-colored rock transform into gleaming steel skyscrapers? How do ancient mountains become modern civilization? Stick around till the end. You'll discover why iron shaped human history more than gold ever did, and the jaw-dropping secret hiding inside every bridge, car, and building around you right now. The story begins in Western Australia's Pilbara region, where iron mountains stretch across landscapes older than dinosaurs. Massive excavators, standing 8 stories tall, picture buildings that walk, tear into rust-red cliffs with bucket teeth weighing 12 tons each. These mechanical giants rip through rock layers formed 3 billion years ago when Earth's oceans first rusted. With thunderous crashes echoing across 40-mile-wide craters, each excavator loads haul trucks carrying 400 tons per trip. That's the weight of 80 elephants moving at 40 miles per hour on tires taller than basketball hoops. Processing 30 million tons annually from single mines, enough iron ore to build 12 Golden Gate bridges every single day. Next comes crushing, where house-sized jaw crushers, imagine dinosaur mouths made of hardened steel, pulverize boulders into gravel-sized chunks. With deafening roars splitting eardrums even through protection, these crushers generate forces exceeding 20,000 pounds per square inch. Clouds of red dust billowing upward create artificial sunsets visible from space satellites. Conveyor belts stretching 12 miles long, longer than Manhattan, transport crushed ore at 18 miles per hour. Workers riding inspection carts traverse distances requiring 25 minutes one way. That's enough belt to wrap around 300 football fields. Every hour, 50,000 tons flow through this system, weight equivalent to 5 Eiffel Towers moving continuously past checkpoints. Giant grinding mills, standing 5 stories tall, with diameters matching Olympic swimming pool widths, pulverize rock into fine powder. Inside these rotating drums, 20-ton steel balls, each weighing more than shipping containers, tumble with ore, creating grinding thunder heard miles away. Operators monitor vibrations. Wrong frequencies mean catastrophic bearing failures, costing millions. At rotation speeds creating gravitational forces triple normal Earth gravity, particles shrink to powder finer than talcum. Processing 8,000 tons hourly, that's filling semi-truck after semi-truck every 30 seconds. This powder, called concentrate, contains 65% iron. Magnetic separators then extract iron particles using forces strong enough to levitate railroad spikes, leaving waste rock behind. Next comes the blast furnace, a towering inferno standing 30 stories high, its steel shell glowing dull orange even from outside. At internal temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize aluminum instantly, iron ore transforms into liquid metal. Picture Dante's Inferno engineered with precision. Measured charges of iron ore, coke, and limestone descend from the top, while superheated air blasts upward at 2,000 degrees from ring-shaped nozzles called tuyeres. This creates a raging chemical storm, where carbon monoxide rips oxygen from iron oxide molecules. The reaction releases enough heat to melt granite. Every 3 minutes, sensors check 20 different parameters. Without precision, furnaces explode with force demolishing city blocks. The blast furnace operates continuously for 15 years, never cooling, never stopping, like Earth's core relocated to industrial facilities. Inside this chemical reactor, materials descend through distinct zones. Upper regions preheat incoming ore. Middle zones drive off moisture and carbon dioxide. Lower depths become hell itself, where iron liquefies. At the hearth bottom, molten iron collects at 2,800 degrees Fahrenheit, dense as lead but flowing like water. Every 4 hours, workers drill through clay-plugged tap holes. Liquid iron erupts in blinding white rivers, flowing through ceramic channels into railroad cars holding 300 tons each. This step is critical because timing determines metal purity. Tap too early, slag contaminates. Too late, furnace pressure ruptures containment walls. After tapping, slag, lighter impurities floating atop molten iron, gets diverted into separate channels. This glowing amber liquid, essentially liquefied rock, contains calcium, silicon, and aluminum oxides stripped from ore. Rather than waste, it becomes roadbed material and cement ingredient recycled at 98% rates globally. The molten iron, called pig iron, contains 4% carbon, too brittle for construction. Picture glass that looks metallic. Drop pig iron from waist height, it shatters into fragments. Next comes the basic oxygen furnace, where pure oxygen blasted at supersonic speeds through 3-foot diameter lances burns away excess carbon in 17 minutes. Flames shooting 70 feet high Temperatures hitting 3,200 degrees create hurricane-force winds inside steel vessels holding 350 tons of liquid metal. Steel making requires precision rivaling brain surgery. Computer-controlled oxygen flow adjusts by milliseconds. Operators add exact amounts of manganese, silicon, chromium, elements changing steel properties dramatically. Too much carbon, steel cracks in winter cold. Too little, metal bends under load. Picture this: alloying elements get injected via submerged lances. Electromagnetic stirring, invisible but powerful, homogenizes composition. Samples extracted every 3 minutes get analyzed via spectrometers, determining chemistry within seconds. Modern furnaces achieve carbon content accuracy to 0.01%, difference between skyscraper standing or collapsing. After refining, liquid steel flows into continuous casting machines producing slabs 30 feet long, weighing 25 tons at rates of 1 slab every 90 seconds. This wasn't always so advanced. Back in ancient Anatolia around 1300 BC, Hittite metallurgists discovered heating iron ore with charcoal produced workable metal. That breakthrough, accidental furnace conditions reaching iron's melting point, changed human civilization forever. Iron tools outperformed bronze, enabling agriculture revolution. The breakthrough came when British inventor Henry Bessemer patented his converter in 1856, slashing steel production time from 24 hours to 17 minutes. Suddenly, steel costs dropped 90%. This single invention built modern cities. Skyscrapers, bridges, railroads exploded across continents. Today, global steel production exceeds 1.9 billion tons annually. That's enough to build 75,000 Eiffel Towers yearly, or manufacture 43 million automobiles, or construct bridges connecting every coastline on Earth. Carbon emissions drop by 62% when using recycled steel versus virgin ore, equivalent to removing 12 million cars annually. Industry saves over $80 billion yearly through scrap recycling. Processing costs drop 43% because melting scrap requires 1/3 the energy of blast furnaces. So here's the secret promised. Every ton of steel you see, bridges, buildings, cars, will be recycled indefinitely. Unlike plastic decomposing into microparticles or paper pulping into mush, steel never degrades. Magnetic separation extracts it perfectly from demolished structures. That girder in your office building might contain steel from 1930s locomotives. Your car's frame could include battleship armor from World War II. Nothing disappears. Metal merely transforms, reborn eternally. From ancient mountains to modern marvels, cycle completes. Iron, humanity's most essential metal, circulates through civilization like blood through veins. We're not consuming Earth's iron, we're borrowing it, briefly, before passing it forward to futures we'll never see.
Inside a steel mill, molten iron glows white at 3,000 degrees. Workers stand 50 feet away. The radiant heat still blisters exposed skin. But look closer at what contains this liquid fire. Gray bricks line the furnace walls, glowing dull orange, yet holding firm. These aren't ordinary bricks. Touch regular clay brick to molten metal and watch it explode into steam and fragments. So what material survives temperatures hotter than volcanic lava? What invisible shield protects every furnace melting metal, making glass, or firing ceramics worldwide? Stay with us. You're about to discover why engineers kill clay to make it stronger, and the counterintuitive secret of double firing that transforms fragile earth into industrial armor, surviving conditions that vaporize steel.
Our story begins in Missouri clay. Deposits formed 60 million years ago when ancient seas deposited aluminum-rich sediments. Excavators rip into hillsides, extracting clay containing over 40% alumina, the magic ingredient. Regular pottery clay melts around 2,000 degrees. High alumina clay? It laughs at 3,000. Watch the extraction crew. They're not just digging dirt, they're harvesting geology's accident. This specific clay formed under precise conditions. Volcanic ash settling through prehistoric oceans, compressed over epochs. The foreman walks the pit daily, examining color and texture. Too much iron content, the clay turns red and weakens. Perfect batches shimmer gray-white, almost ghostly. Every ton supports industries most people never see, but everyone depends on.
The clay arrives at processing facilities caked with impurities. Massive crushers reduce house-sized boulders to gravel. Water floods the mixture, creating liquid slurry pumped through magnetic separators. Powerful magnets extract iron particles. Even microscopic contamination causes problems later when heat turns iron into weak spots. Picture the filtration building. Workers monitor screens showing particle sizes measured in microns. The slurry flows through increasingly fine meshes, removing everything except pure clay molecules. The process mirrors diamond cutting, patient, meticulous, unforgiving. One foreman's been doing this 30 years. Clay's honest, he says. Screw up purification, the furnace tells you months later when bricks fail. By then, you've shut down a steel mill.
Here's where it gets strange. Before making bricks, they destroy the clay. Giant kilns, tunnel ovens stretching 300 feet, fire raw clay at 2,400 degrees. The material transforms. Water molecules trapped in crystal structure evaporate. Crystals fuse together. The clay dies, becoming chamote, fired aggregate resembling brown gravel. Watch workers dump glowing chamote onto cooling floors. Steam erupts as residual moisture hits air. The material has lost its plasticity forever. You can't reshape it. You can't mold it. Ancient potters would call this ruined clay. Modern engineers call it the secret ingredient. This dead material becomes the skeleton that prevents shrinkage when the final brick gets fired. It's already survived hell once, it won't flinch the second time.
Now the resurrection begins. Crushers pulverize chamotte into particles ranging from sand size to powder. Meanwhile, fresh raw clay gets mixed with water, creating a binding paste. The ratio matters obsessively. 70% dead chamotte, 30% living clay. Too much chamotte, the brick crumbles. Too little, it shrinks catastrophically during final firing. Imagine construction workers mixing concrete, but every batch costs thousands, and failure means industrial catastrophe. The mixing drums rotate for 40 minutes. Technicians pull samples constantly, checking consistency. The mixture emerges as damp, grainy paste. Looks like chunky peanut butter, but feels like dense sand. This strange hybrid contains both the dead and the living, the fired and the raw, the stable and the flexible.
Hydraulic presses generate forces exceeding 2,000 tons, compressing the clay chamotte mixture into brick shapes. The pressure is critical. It determines density, which determines strength. Watch the press operator. He's worked this machine 18 years. His hands hover over emergency stops, eyes tracking pressure gauges. The bricks emerge slightly damp, surprisingly fragile. You could break one with a hammer. Workers stack them on kiln cars, steel platforms holding thousands of bricks. The cars roll into drying chambers where warm air removes moisture over 72 hours. Dry too fast, surface cracks. Too slow, production bottlenecks. The drying supervisor walks the chambers constantly, adjusting airflow by feel and decades of experience.
The final firing begins. Kiln cars enter tunnel kilns heated to 2,600 degrees. The journey takes 48 hours, crawling through zones of increasing temperature. In the first zone, remaining moisture evaporates. Second zone, raw clay begins sintering, particles fusing at edges. The critical third zone pushes temperatures beyond anything the bricks will face in service. You can't see inside operating kilns. The heat would blind you instantly. But infrared cameras reveal the transformation. The bricks glow yellow, then white. At peak temperature, individual clay particles fuse into dense ceramic matrix. The chamotte, already fired once, provides dimensional stability, preventing the shrinkage that would crack ordinary clay. When bricks finally exit, they've transformed into material that will outlast the furnaces they protect. Quality control seems simple. Drop the brick. It should ring like a bell. Clear, sustained tone indicates proper firing and density. Dull thuds mean hidden cracks or insufficient firing. Experienced inspectors can diagnose problems from sound alone. "That's a Saturday brick," one inspector says, tapping a dull specimen. "Someone rushed the firing before weekend. Rejected." But sound testing is just the start. Samples get crushed in hydraulic presses, measuring compressive strength exceeding 10,000 psi. Others get thermal shocked, heated to 2,000 degrees, then water quenched. Survivors prove they'll handle the brutal thermal cycling of industrial furnaces. Failure rate must stay below 0.5%. Even one weak brick can collapse a furnace wall, causing million-dollar shutdowns.
Refractory technology emerged from ancient pottery kilns. Early Chinese potters discovered high alumina clay fired harder than anything else. By 1300 AD, Chinese furnaces using primitive refractories reached temperatures melting iron, a feat Europeans wouldn't match for 4 centuries. The Industrial Revolution demanded better. In 1879, Sidney Gilchrist Thomas invented basic refractory lining, enabling the Bessemer process to use phosphorus-rich iron ore. Suddenly, Britain's massive ore deposits became viable. The discovery shifted global power. Whoever controlled refractory technology controlled steel production. Today, specialized refractories enable everything from semiconductor manufacturing to rocket engines. The global industry moves 50 million tons annually. Invisible infrastructure supporting visible civilization.
Carbon emissions dropped 41% using modern refractories versus 1950s technology. Better insulation means less fuel heating furnaces. Industry saves $78 billion annually through extended furnace life. Modern refractories last 5 years versus 6 months for old materials, slashing replacement costs. Here's the secret we promised. Refractory bricks work because they're already dead. That double firing process, burning the clay into chamotte, then mixing it with fresh clay and firing again, creates material that's experienced worse than anything it'll face. The chamotte has no shrinkage left to give. The fresh clay binds it together, then dyes itself during final firing, becoming equally stable. From ancient clay to modern armor, the cycle completes. We've learned that sometimes strength requires destruction first. Kill the material, resurrect it, kill it again. Only then does it become immortal, standing guard in furnaces that never sleep, protecting the industrial processes keeping civilization running. That humble gray brick isn't just holding back heat, it's holding back chaos. Stand beside the world's largest diesel engine. It towers 44 feet tall, higher than a 4-story building, stretches 89 feet long, longer than a semi-truck with trailer. 14 cylinders, each wider than oil drum, fire in sequence, producing 109,000 horsepower. That's the power of 1,600 cars, concentrated in one single machine. This engine burns 250 tons of fuel daily, moving 20,000 containers across oceans at 23 knots. How does metal combusting heavy fuel oil generate force pushing 90,000-ton ships through water? Why build engines this enormous when smaller multiples could work? Stay with us. You'll discover the brutal elegance of two-stroke combustion at massive scale
And the shocking secret of why these engines burn fuel refineries consider waste. The cheapest, dirtiest Our journey begins at Hyundai Heavy Industries in Ulsan, South Korea, the shipyard building these mechanical titans. The engine manufacturing hall spans 30 acres under single roof. Overhead cranes rated at 600 tons glide on rails, positioning cylinder blocks weighing as much as locomotives. Workers look like ants beside components. Watch the cylinder casting. Molten iron pours into sand molds, creating a single cylinder liner. Hollow tubes where pistons travel. Each liner stands 12 feet tall, walls 4 inches thick. The iron must cool for 72 hours. Rush it. Thermal stresses create microscopic cracks that propagate under operation, causing catastrophic failure. We make engines that run 30 years continuously, explains Chief Engineer. No second chances if casting fails.
The crankshaft arrives on specialized trucks, a single forged steel shaft weighing 300 tons, machined to tolerances measured in thousands of inches across 70-foot length. Installing it requires choreographed precision. Hydraulic jacks lift the shaft while technicians align bearing surfaces. One misalignment of ½ inch causes bearing failure within weeks of operation. Picture the assembly floor. 14 cylinder liners bolt to engine block, itself a 40-foot steel casting, forming engine skeleton. Each connection uses bolts diameter of baseball bats, torqued to specifications requiring pneumatic impact wrenches lasting 5 minutes per bolt. Assembly takes 6 months, 12-hour shifts, teams of 50 engineers and technicians. One finished engine represents 200,000 man-hours, equivalent of one person working full-time for 96 years straight.
The pistons dwarf automobile engines. Each piston assembly, piston, rings, and connecting rod weighs 6 tons. That's heavier than full-sized pickup truck. The piston crown, exposed to combustion, endures temperatures exceeding 1,800 degrees and pressures reaching 2,000 psi. Material science pushes limits here. Watch piston installation. Cranes lower assemblies through cylinder tops. Workers guide them onto connecting rod bearings with millimeter precision. The piston rings, spring steel bands sealing combustion pressure, get installed by hand. Each ring expands under tension, slip during installation, and the ring snaps, injuring workers and destroying components worth $50,000. Veterans develop feel for tension, installing rings quickly yet carefully. 20 years I've installed 3,000 pistons, says one assembler. Still respect every one.
Now grasp two-stroke operation. Elegantly simple, yet counterintuitive. Unlike car engines firing every other rotation, marine diesels fire every rotation. As piston descends, it uncovers ports in cylinder wall. Compressed air rushes in, pushing exhaust out simultaneously. The piston rises, compressing fresh air. Near top, injectors spray heavy fuel oil. Compression heat, not spark plugs, ignites fuel. Explosion drives piston down. The cycle repeats. This two-stroke design eliminates valves entirely. No camshafts, no timing chains. Fewer parts mean greater reliability. But it demands supercharging. Turbocharges forcing air into cylinders at 22 psi. Without pressurization, the engine wouldn't breathe. Turbochargers the size of sedans spin at 20,000 RPM, driven by exhaust gas. They glow red-hot during operation, requiring water cooling systems circulating thousands of gallons hourly. Fuel injection happens at extreme precision. Each cylinder consumes 16 gallons per combustion cycle, enough to fill your car's tank every few seconds. Injectors spray fuel as fine mist under 6,000 psi pressure. The atomization must be perfect. Droplets too large won't burn completely, wasting fuel. Too fine, combustion becomes explosive rather than controlled, damaging engine. The fuel itself surprises people. These engines burn heavy fuel oil, basically petroleum refinery leftovers, after extracting gasoline, diesel, and jet fuel. It's thick as molasses at room temperature, must be heated to 240 degrees before flowing. Contains sulfur, metals, and contaminants that would destroy car engines instantly. But marine diesels tolerate it because economics dictate everything. Heavy fuel costs 40% less than automotive diesel. At 250 tons daily, that price difference means millions saved annually per ship.
Engine control happens from bridge via computer systems monitoring 600 parameters simultaneously. Engineers track cylinder temperatures, bearing pressures, fuel consumption, turbocharger speeds. The engine room, 3 decks tall, deafeningly loud despite ear protection, houses the mechanical orchestra. Walk the engine room during operation. Heat radiates from every surface. Metal creaks and groans as thermal expansion moves components fractions of inches. Across a 70-foot engine, that's feet of total movement. The crankshaft, visible through inspection ports, spins at 102 RPM. Seems slow until you realize this massive shaft accelerates tons of metal from 0 to maximum speed every single rotation. The forces involved bend physics. One chief engineer describes it, "This isn't machinery, it's controlled violence. We're detonating tons of fuel hourly inside metal box, converting explosions into rotation." Maintenance happens at sea on schedules measured in years. Every 8,000 hours, roughly 1 year of operation, crews perform major service. They drain lubricating oil, 60,000 gallons per engine, replacing filters the size of trash cans. Inspect cylinder liners for wear using ultrasonic equipment. Pull pistons for ring replacement. The most dramatic maintenance involves crankshaft inspection. Engineers use magnetic particle testing, apply magnetic field, spray iron particles, look for cracks where particles accumulate. Finding cracks in 300-ton crankshaft spinning at 100 RPM means potential catastrophic failure. The process takes 4 days of continuous work while ship sits idle, losing $200,000 daily in lost revenue. But catching cracks before failure saves the engine worth $15 million. No shortcuts exist. We maintain like lives depend on it, states Chief Engineer, because they do.
Rudolf Diesel invented compression ignition engines in 1897, demonstrating fuel efficiency double that of gasoline engines. His original design ran on peanut oil. Diesel envisioned farmers powering equipment from crop byproducts. The petroleum industry hijacked his invention, optimizing for their cheapest product, heavy fuel oil. Marine applications began in 1920s. By 50s, diesel surpassed steam turbines. The two-stroke design, perfected by Sulzer and Wärtsilä through 70s and 80s, became dominant. Today's largest, the Wärtsilä-Sulzer RTA96C, produces power exceeding small city power plants. Just 14 cylinders generating 109,000 horsepower. 23,000 containers moved by single engine. 98% of ocean cargo moves via diesel-powered ships. These engines literally keep global economy flowing.
Carbon emissions seem paradoxical. These engines burn dirtiest fuel, yet achieve 48% thermal efficiency, converting nearly half consumed energy into motion. Modern cars manage 25%. The efficiency comes from slow operation and massive scale, allowing effective heat recovery through turbochargers and economizers. Here's the secret we promised. Marine diesels burn fuel refineries would otherwise struggle disposing. That heavy fuel oil, thick, contaminated, full of sulfur, represents petroleum industry's bottom-of-barrel waste. Refineries initially paid ships to remove it. Marine engines transformed waste into commodity. Today, Heavy fuel powers 90% of ocean shipping. Those engines, burning waste, move 60 billion tons of cargo annually, generating 3% of global carbon emissions, while handling 90% of international trade. From refinery waste to global commerce, the cycle completes. We've built machines so large they boggle comprehension, burning fuel so crude it seems impossible, moving cargo quantities that dwarf imagination. That container ship horizon, powered by controlled explosions in cylinders taller than you, spinning crankshafts heavier than your house, burning fuel thicker than syrup. Engineering at scale where normal physics seems inadequate, yet it works reliably, efficiently, endlessly. These aren't just engines, they're the beating hearts of globalization itself.
Every year, over 40 million new gadgets hit the market, but almost nobody knows about the metal that makes them actually work. Why can a tiny element buried deep underground literally launch an entire civilization, from the Bronze Age to modern electronics? And what do ancient swords, tin cans, and your smartphone have in common? In this video, we're uncovering the secret of tin, the metal that built the past, runs the present, and hides a fact you've definitely never heard before. Stick around until the end. That's where the real mystery reveals itself. Tin isn't just some new trend. This is a metal with a deep-rooted history spanning thousands of years. Its discovery sparked a genuine revolution that forever transformed the course of human civilization, launching what we call the Bronze Age. Picture this. Ancient craftsmen learned to extract copper and forge tools from it. But copper was soft. Then, whether by accident or experimentation, they discovered something remarkable. If you added a little bit of another then unknown metal to molten copper, tin, the alloy became incredibly strong, hard, easier to cast, and held a sharper edge. That metal was tin. The copper-tin alloy became known as bronze. Bronze swords, shields, tools, jewelry, all of this suddenly became accessible, giving ancient civilizations a massive advantage. It was a true technological leap that transformed warfare, agriculture, and art. Tin became so valuable that real battles were fought over its deposits, and trade routes to tin mines, like those in Cornwall, Britain, were incredibly important. Over the centuries, tin stayed valuable. It was used as a coating for other metals to protect them from corrosion. For example, tin plate, a thin sheet of steel coated with tin, which was used to make cans. It was also used to make soft solders that joined metals together, and in the production of mirrors, and even to create organ pipes and coins. But its true renaissance came in the 20th century with the rise of electronics. Over 50% of all global tin consumption goes to this industry. Solder. That's its main job. Your computer, smartphone, TV, inside them, thousands of electrical components are connected together. These connections are made using solder, which is usually an alloy of tin with other metals, like lead in the past, now mostly with copper, silver, or nickel. Tin is perfect for solder because it has a relatively low melting point, which makes it easy to melt and form connections without damaging sensitive electronic components. Tin also wets metals, meaning it easily flows across the surface, creating a strong electrical and mechanical bond. It's got great electrical conductivity too, and it's corrosion resistant.
Modern electronics use what's called lead-free solder, which is a huge step forward for the environment. Tin is the main component in these alloys. Without reliable soldered connections, the entire complex architecture of microchips would simply fall apart, and your gadget would turn into a pile of useless parts. Tin is used to coat other metals, especially copper, on printed circuit boards. This protects the copper traces from oxidation and makes the soldering process easier. It's also used to coat connectors, which improves their electrical conductivity and corrosion resistance. Tin isn't a super common element in the Earth's crust. Its primary mineral is cassiterite, basically tin oxide. It's a pretty dense mineral that's often found in placer deposits,
meaning you can extract it from river sediments or ancient coastlines. Over 70% of the world's tin production is concentrated in 4 countries across Southeast Asia and South America: China, Indonesia, Myanmar, and Peru. This makes the tin market highly sensitive to political and economic events in these regions. Tin mining begins with the exploration phase. Geologists, armed with modern technology, conduct surveys, drilling, and analysis of soil and rock samples to find locations where cassiterite concentrations are high enough for economically viable extraction. Once a deposit is identified, development begins, which can follow 2 main paths depending on the type of deposit. The first and most common method of tin mining is from placer deposits. Picture this. Over millions of years, cassiterite washed from bedrock by water and erosion accumulated in riverbeds, at the bottom of lakes, or on ancient seashores.
It settled like sand in what's called placer deposits. Extracting from these deposits is often way simpler than digging underground mines. Here, they use massive dredges, floating factories that scoop up tons of soil and gravel from the bottom of waterways, or they deploy hydraulic monitors, powerful jets of water under high pressure that blast away soil from riverbanks or hillsides containing cassiterite. The blasted rock then flows to primary processing, where gravity methods, exploiting density differences, separate the cassiterite from lighter waste rock. Think industrial-scale gold panning, only gigantic. The second method? Extracting from primary deposits, where cassiterite sits directly in solid rock. That's where traditional underground mines come in, same as mining any other metal.
Miners drill tunnels and boreholes into the rock, use explosives to blast apart the ore vein, then loaders collect the ore and haul it to the surface. It's a more expensive and complex operation, requiring heavy-duty equipment and strict safety protocols. Once extracted, the ore, no matter where it came from, heads to a processing plant. First, it's crushed and ground into a very fine powder in mills to free the cassiterite crystals from the surrounding rock. Then various enrichment methods kick in. The first method, gravity separation. Since cassiterite is a pretty dense mineral, it gets separated from lighter minerals using water. This can happen in jigs, concentration tables, or spiral separators. The second method is flotation. Sometimes, for further enrichment or to separate cassiterite from other minerals, flotation is used, where cassiterite selectively sticks to air bubbles and rises to the surface as foam. As a result of all these processes, a tin concentrate is obtained that already contains more than 50% cassiterite, or even more. This concentrate then goes to a metallurgical plant to produce pure metallic tin. Here, the concentrate, which is tin oxide, is mixed with coal, which acts as a reducing agent, and fluxes. Fluxes are substances that help separate impurities. This mixture is heated in special furnaces to high temperatures, typically around 2400 degrees Fahrenheit. At these temperatures, the carbon steals the oxygen from the tin oxide, releasing pure metallic tin, which melts and flows to the bottom of the furnace. The molten crude tin still contains impurities from other metals, so it goes through another crucial stage, refining. This can be thermopurification, where the lead is heated to specific temperatures so other metals separate out or float to the surface. Or more often, electrolytic refining, which allows for extremely high tin purity. High purity means almost 100% in this case. Can you believe that? This is critically important, especially for the electronics industry, where even the tiniest impurities can affect conductivity and component reliability.
A machine capable of squeezing metal like it's alive, not melting it, not breaking it, but forcing it to flow under pressure that's impossible to imagine. 80,000 tons of force concentrated at a single point. That's more than the weight of an entire army of tanks stacked on top of each other. But why does humanity need such inhumane power? And why is this giant hidden deep underground, as if they're deliberately trying to keep it out of sight? Under this press, they're not just making metal parts, they're forming the heart of airplanes, rockets, and reactors without a single welded seam. But there's one fact almost never discussed publicly. If you watch till the end, you'll understand why this press isn't an engineering marvel, but a tool of global dominance.
How much is 80,000 tons? Just to put that in perspective, that's the equivalent weight of 80,000 cars compressed into a single point, or the pressure created by an entire army of giant elephants stacked on top of each other. This metal colossus, installed in 2013, is the world's most powerful forging press, surpassing all previous achievements. It's a true giant, reaching the height of a 10-story building. Its foundation is buried deep in the ground, while its upper section rises into the sky like an industrial skyscraper. It looks like a machine from a science fiction movie, but it's absolutely real and performs its incredible work every single day. This press is designed for stamping extraordinarily large and complex parts that are critically important for the aviation, aerospace, and energy industries. These can be massive panels for rocket bodies, huge wing or fuselage components for aircraft, turbine parts for power plants, or even reactor equipment.
The story of these giant presses is its own epic saga, deeply intertwined with the Cold War era. Back when the USA and USSR were competing for dominance in the space race and military industry, there arose a need for super strong, seamless metal structures. The Americans were first to build presses with a capacity of 50,000 tons, allowing them to create large aircraft components without welds, drastically improving reliability. The Soviet Union wasted no time responding, creating an even more powerful 75,000-ton press that also became a legend of engineering ingenuity. These titans of their time represented the pinnacle of metallurgical technology, symbols of engineering superiority and the industrial might of superpowers. They were true monsters, capable of shaping metal with such force it seemed almost impossible.
But this modern Chinese press shattered all those records, surpassing even the Soviet giant. It can crush metal with literally superhuman force. Under this press, red-hot metal blanks weighing hundreds of tons, that's like dozens of trucks compressed into a single chunk of metal, get flattened like soft clay. Metal heated to a red or yellow glow undergoes incredible pressure. It doesn't just deform, it flows under this colossal force, slowly but relentlessly taking on the required pre-designed shape. This isn't casting, this is forging, a process that strengthens the metal structure, making it denser and stronger than any cast piece. This ability to produce solid forgings of enormous size is the main advantage and defining characteristic of such presses. Picture this. You can get a massive spar for an aircraft wing or a reactor vessel component without a single weld.
Weld seams, no matter how high quality they are, will always be potential weak points in metal structures. They can be sites of stress concentration, cracks, or corrosion. In mission-critical components, where the cost of failure can be catastrophic, say in an aircraft at 33,000 feet, or in a space rocket, the absence of weld seams isn't just desirable, it's absolutely essential. Solid forgings, formed under such pressure, have unmatched strength, uniform structure, and maximum reliability. They're the foundation for building supersonic aircraft, ultra-powerful rockets, spacecraft, and safe nuclear reactors. To install a press of this magnitude, you don't just build a foundation, you build an entire underground iceberg. The main structure of the press is buried deep in the earth, because the enormous forces acting during forging create incredible vibrations that need to be absorbed. It's like building a foundation for a skyscraper, but in reverse, plunging into the depths of the earth for dozens of feet.
Installing equipment like this is a more complex logistical operation than launching a space rocket. Press components arrive on site by the hundreds, then get assembled using giant cranes and engineering teams working for years. By the way, an 80,000-ton press force isn't just pressure, it's a controlled transformation of material at the micro level. Under that kind of force, the metal's crystalline structure changes. Grains become finer and denser, giving it exceptional mechanical properties. It's like leveling up metal to maximum stats. Here's another thing. Running a giant like this takes a colossal amount of energy. This isn't just plug it into an outlet. Powering the hydraulic pumps and maintaining stable pressure requires a dedicated power plant.
And the cooling systems that carry heat away from the hydraulic fluid, just as critical. Under these loads, the oil can get seriously hot. It's a true engineering ecosystem where every single component is mission critical for the entire complex to function. As we mentioned, instead of welding together dozens of small metal sheets, the press can forge a significant portion of the shell from a single block of metal. This makes the structure lighter, stronger, and far more resistant to fatigue. While the press doesn't stamp out tiny turbine blades, it can form large casing components for jet engines, parts that withstand extreme pressure and temperature.
Beyond aerospace, where every single pound and every hairline crack can spell disaster, this press also stamps out components for nuclear and thermal power plants. We're talking ultra-high strength reactor housings and lids, turbine elements, generators, and other equipment operating under extreme pressure, temperature, and radiation. Here, integrity and zero defects aren't just about efficiency, they're about protecting entire regions. They also forge shafts and rotors for massive ships and industrial machinery. Enormous turbine installations on ocean-going vessels or in power generation require ultra-strong shafts that can handle colossal rotational forces and torsional loads. Forgings made under this press are perfectly suited for these purposes.
Watch liquid steel pour from a ladle, glowing white at 3,000 degrees, bright enough to burn your retinas instantly. 20 tons cascading like luminous waterfall into molds, each splash throwing sparks 50 feet. This isn't new steel from ore, it's recycled. Yesterday's junked cars, demolished buildings, scrapped appliances melted and reborn. America recycles 80 million tons of steel annually, more than all other materials combined. That rebar in your building's foundation? Average age, 73 years through 4 previous lives. How does rusted scrap transform into structural steel stronger than original? Why does recycled steel outperform virgin steel in crucial applications? Stay with us. You'll witness industrial-scale alchemy turning garbage into skyscrapers and discover steel's shocking secret. It's infinitely recyclable without quality loss, forever. Nucor Steel's Berkeley facility in South Carolina processes 3 million tons annually, enough steel to build 15 Golden Gate bridges yearly. The scrapyard stretches half a mile, mountains of metal sorted by type. Shredded cars pile 6 stories high. Railroad rails stack like pickup sticks. Crushed appliances form metal glaciers. Giant cranes with electromagnets strong enough to lift entire automobiles move continuously, sorting, stacking, organizing chaos. Watch the shredder operation. A hammer mill the size of 2-story house contains rotating drum with 50 hammers, each weighing 300 pounds. Cars feed in whole, no disassembly required. In 8 seconds, automobile becomes fist-sized chunks. The noise defies description, continuous thunder as metal destroys metal. The shredder processes 100 cars hourly, 6,000 monthly. Every junked vehicle in America eventually passes through facilities like this. Nothing wastes. Even copper wiring gets separated and recycled independently. The electric arc furnace, EAF, is where steel is reborn. This vessel, 40 feet diameter and 30 feet deep, operates through electrical violence. 3 graphite electrodes, each 2 feet thick and 15 feet long, descend from the roof. When power flows, 90 megawatts, enough electricity for 70,000 homes, arcs jump between electrodes and scrap, generating temperatures exceeding 5,000 degrees. The initial charge contains 200 tons of scrap steel loaded via overhead buckets. Operators lower electrodes carefully. Too fast, they shatter. Too slow, productivity suffers. The arc strikes with deafening crack. Visible through protective glass is blinding white plasma. Metal begins melting immediately. The sound evolves from cracking to roaring as molten pool forms. Watching through infrared cameras reveals the chaos. Solid metal liquefying, impurities rising as slag. The melt cycle takes 45 minutes start to finish. Chemistry happens through violence and precision simultaneously. Oxygen lances inject pure oxygen into molten steel at supersonic speeds. The oxygen burns impurities, carbon, sulfur, phosphorus, creating slag that floats atop the denser steel. Temperature reaches 5,800 degrees at plasma core, hot enough to vaporize iron itself. Cooling water circulates through furnace walls at 5,000 gallons per minute, preventing meltdown. Alloying additions fine-tune steel composition. Computer-controlled systems add precise amounts of manganese, chromium, nickel, elements determining final properties. High-strength rebar requires different chemistry than structural beams. The metallurgist's console displays real-time analysis via spectrometer. Laser vaporizes steel sample. Computer analyzes emitted light, identifying every element present to parts per million accuracy. Adjustments happen in real time. Chemistry perfected before tapping begins. Tapping releases the dragon. The furnace tilts hydraulically, massive vessel rotating on trunnions. Molten steel pours through tap hole into waiting ladle. Refractory-lined bucket containing 40 tons of liquid metal. The pour takes 6 minutes. Continuous stream of glowing steel creating updrafts so powerful, they lift dust and debris into the air. The temperature, 3,050 degrees, radiates heat felt 200 feet away. The ladle, mounted on railcar, travels to continuous caster. This machine revolutionized steelmaking, replacing individual mold casting with endless process. Molten steel flows from ladle into tundish, then into water-cooled copper molds oscillating up and down. As steel contacts mold, outer shell solidifies while interior remains molten. The strand, continuous ribbon of steel 8 inches square, emerges from bottom at controlled speed, bent gradually from vertical to horizontal through roller system. The hot rolling mill is where shape is born. The continuous cast billet, still glowing red at 2,000 degrees, enters the roughing mill. Giant rollers, each weighing 30 tons, squeeze the steel, reducing thickness while increasing length. The transformation is violent. 8-inch square becomes flat bar 6 feet wide and 1/4 inch thick in 7 passes through successive roller stands. Watch the mill operation. The steel screams through at 40 miles per hour, extending like taffy as rollers compress it. Water jets cool rollers constantly. Without cooling, the steel would weld itself to roller surfaces. Scale. Iron oxide forming on surface gets blasted away by high-pressure water, creating permanent rainbow mist in the mill. The noise is beyond hearing protection. Low-frequency vibration felt in bones. One operator describes it. Steel doesn't want to be flat. We convince it otherwise through controlled violence. Cooling determines final properties through metallurgical magic. After final rolling pass, steel enters cooling bed, where water jets precisely control cooling rate. Fast cooling creates hard, brittle steel. Slow cooling produces soft, ductile steel. Controlled cooling, varying rates across thickness, creates exactly desired microstructure. Computer systems adjust water flow based on steel grade, thickness, ambient temperature. The coiler winds finished steel into massive coils, 40 inches wide, 1 mile long, weighing 25 tons. These coils ship to manufacturers producing everything from automobiles to appliances. Some steel goes to galvanizing lines where molten zinc coating prevents rust. Other steel gets further processed, cold rolled for precision applications, annealed for formability. But the core material, recycled steel, remains unchanged, ready for another century of service. Steel recycling accelerated during World War II when scrap drives collected every available piece of metal for weapons production. Post-war, technological advances made recycling economically viable. The electric arc furnace, developed in 1960s, eliminated need for iron ore. Recycling became primary production method. By 1980s, mini-mills using EAF technology revolutionized the industry, undercutting integrated mills using blast furnaces. Today, America produces 70% of steel from recycled scrap. Traditional integrated mills using iron ore and blast furnaces still exist but increasingly rely on scrap supplementation. The transition reflects economic and environmental reality. Recycling uses 60% less energy than primary production. A single steel mill prevents mining hundreds of thousands of tons of iron ore annually. The industry transformed from extraction to circulation, steel cycling endlessly through economy. Carbon emissions dropped 65% using recycled steel versus virgin production. Industry saves $58 billion annually avoiding ore mining and processing. Each recycled ton prevents 4 tons of raw material extraction, ore, coal, limestone combined. Here's the secret we promised. Steel is infinitely recyclable without degradation. Unlike plastic degrading with each recycle, steel maintains properties indefinitely. That nail holding your wall could have been Roman sword, railroad spike, Model T chassis, World War II tank, 1960s Cadillac, demolished skyscraper, and now construction steel. Same iron atom serving humanity for millennia. The crystal structure reforms perfectly during melting, erasing all history. Impurities burn away in the furnace, chemistry optimized through modern metallurgy. From junkyard to job site, the transformation completes. We've created closed-loop system where waste becomes resource, garbage becomes infrastructure. That bridge you drove across, those rails carrying freight, the frame supporting your office, all contain steel recycled dozens of times. The metal never tires, never weakens, never remembers its past. We've mastered material that improves through use, strengthened by human engineering beyond nature's intention. Steel isn't consumed. It circulates, eternally useful, permanently valuable, waiting only to be reshaped for next purpose. Civilization built on metal that refuses to die.